The first speaker is Jun-Yan from CMU. He's trying to introduce the enabling collaborations between creators and generative models. So welcome.
Yeah, thanks. Yeah. Great. Thanks. It's great to be here. Did that close? Today I'll just talk about some our recent work on enabling collaboration between creators and generative models. Okay, so I want to go back to 2016, which we kind of wrote one of the first generative models paper in a computer vision conference. Here we try to turn user scribbles to some photos. Okay. Around the same time, we see a paper from Ruslan's group, who is currently faculty at CMU as well. Actually, maybe I don't need the. So I can. So I can hear myself. Oh, I see. So I can hear myself. It's very weird. Can we get that over? Better? Okay, it's slightly better. Okay, that's much better actually for me. So at the same time, we saw a paper from Ross group from University of Toronto, but he's a faculty at CMU now as well. So he and his students was building a system, one of the first deep learning system for text-to-image generation. That's around 2016. I remember we were reading this paper, at UC Berkeley's reading group, and everybody was laughing at the idea. Why does anyone want to work on that? This is never going to work. Maybe this is going to work by the end of our career. Maybe 2050s, 2040s. So again, but we're still working on the same problem. We have been working on generative models for almost a decade. But we try to work on something simpler. Let's say we don't have text, but we try to transform a sketch into a photo, and this is the idea behind Pix2Pix, led by Faith Pisola, who is currently faculty at MIT. In Pix2Pix, you can generate image with simple user scribbles. This is around 2016, December 2016. You can generate an image, and this is the images we are generating. Almost like a decade ago, so it's only cats, right? You don't need any text problem. You cannot generate dogs, Okay, and then we were working on to make this method more kind of unsupervised in a sense, since we don't have horse and zebra pairs. How can we learn the transformation without accessing to the pair data? And this is the idea of CycleGAN. And in CycleGAN, you can transform a photo into different style, like some Western style, this ukiyo-e style in Japan. You can even translate a painting back to a photo that also works. This is the idea behind CycleGAN. You can transform a horse into a zebra. And people say, why do you want to do that? But you can learn other type of filters as well. We'll keep working on that. In 2019, we collaborate with NVIDIA, and we try to generalize to more categories. Maybe we'll go from one category like cat to 20 categories. We did a demo at SIGGRAPH real-time live. It's a real-time demo, so in front of thousands of people. And this is actually the first time a deep learning system win the SIGGRAPH like a real-time live demo awards. Okay, and you can generate, like mountains, like oceans, skies, clouds, like that. Okay, and more recently we have been also working with diffusion model, and this is the paper we collaborate with Stanford. Given an equal image and a text prompt, you can generate an image according to the user's inputs, right? And maybe you have like kids drawings, and you can transform it into interesting style. Okay. So since the invention of SDEdit, lots of better methods was proposed, such as instruct Pix and ControlNet, which are very popular ways of doing image conditioning generations. Recently, we combined the idea behind Pix2Pix and this control net kind of stuff. You can actually train a model to generate an image in real time with diffusion model. You can pre-train a pre-trained diffusion model into one-step generator. This allows you to generate a cat. But this time we can support text prompt, so you can try different type of text prompt like black cat, white cat. If you are not a cat person, you can also try dog. If you are not a cat person. Okay. So now in 2025, it seems like everybody was working on generative models. It's kind of become a very popular or kind of trendy area. And in some sense, I found it's very hard to publish a paper in 2016 because nobody care about it. It's very hard to get your paper accepted. But now it's also very hard for my students to get paper accepted because everybody is working on that. Like if you have an idea, you might see archive paper next week. So it works too well now in some sense. So you want something in between, right? But anyway, we can generate a toilet now, which is kind of working. You can potentially use it, but better than the 2016 toilet. So I think one day, maybe a few years ago, my wife came to me and say, "Oh, do you guys work on generative AI?" Like, what is generative AI? I work on generative models. I don't know what is generative AI. And then I realized if you change everything to AI, it's just easier to raise funding, for companies, maybe for the universities as well. So anyway, but in some sense, the generative AI it looks like a magic, right? It can generate all kinds of very interesting images. The image was coming from the models, coming from a generative model, and the model was trained on billions of images, right? The model was trained on billions of images, 10 billions of images. And importantly, one thing people don't talk about these days is these just training images come from contributors, like human contributors, like artists, designers, photographers. You take a photo of your family members, somehow that become a part of the training images. So people, and we can look at, right, if the people who train the models get paid pretty well, and the people who can sell GPUs also get paid pretty well, but the contributors of the training images, they often don't get paid at all. Okay, so I think when people are excited about this technology, we need to acknowledge that there are certain group of people who are very upset about this technology. So as a result, there are lots of ongoing legal battles in the US. Lots of artists were suing all the startups who use their images without their permissions. Oftentimes, you can actually, for example, the model tend to memorize the training images. So you can actually, the Berkeley/Google paper found out the model can reproduce exactly the same images which are in the training set. So the model was learned to memorize the images. In the US, the court says you cannot copyright AI generated images, which kind of makes sense. There are also lots of kind of negative feeling against generative AI in the creators industry, like the movie industry. People are against the use of large language model for writing a movie script. People are also against using of the actor or actress like portraits rights for the future movies. And digital artists are pushing against the idea of using generative AI, so they have this movement of saying no to AI. If you read their statements, so I'll make it bigger. I quote, so my artwork is used to train these generators without my consent, right? Nobody send me an email, so can I use your images? No. And I get zero, composition, even credits. You don't even get credits. There are no compensation for the use of my art, even though this generator costs money to use, right? The generator was trained on the artist's work and was actually trying to replace our artist's jobs. Okay, and importantly, most of the artists, right, in anywhere in the world, are not making that much money. They are not like AI researchers, like making like it's a meta lab, right? They're not making that much money, so they are making like an average, income, like average income, right? So the artist is not a profitable job for most of people, except the very famous one. So now, if you reduce income, they can barely, support their families in some sense. Okay. And so, in short, the generative model uses trained data of artists, photographers, and creators without their consent, and also without paying for them, or even without giving them credits, right? You may think, oh, maybe we are not artists, so we are not worried about it. But in some sense, we are worried about it. For example, if someone upload the photos of their babies to some website and the baby's photo got trained on these models, it's kind of scary. Okay. So if you look at these copyright issues, here is the image. This is the guy. So yeah, this image is very interesting in some sense. So no, there's something called like this is the real image, this is the fake image, this is the generated images, and you can see the Getty images. You can see the Getty images here. It's the Getty images is the website to host these images. This is AI. AI is actually one of the leading insurance company in Europe who supports this. If you watch football, this is Spurs FC. This player is I believe is Christian Eriksen, who is a former player of Spurs FC. So in this image, we kind of violate 4 types of rights. And if you look at this this is the Greg Rutkowski. His name has been, he is a very famous prompt. His name is a very famous prompt in the Gen AI community, because you can just type his name, say I want to generate image in the style of Greg Rutkowski. So his name became the most popular artist prompt in the entire community. It's not like Van Gogh or anyone like that. It's his name, and his name has been used by more than 500,000 times in 1 or 2 months. So he is not very happy about that. He has not been, he is still a living artist, right? In some sense, he want to make money out of his own work. Now everybody can generate his work, so his artwork's value got diminished. Okay, so he was also suing all the startups, suing all the generative AI startups. Okay, and in some sense, if you evaluate someone's copyright, well, if you write this kind of replicate, if you evaluate replicate copyright, their company will also sue you, right? In some sense, if you make a coffee cup with replicate photos, you might lose lawsuit for like $700,000. So now the question is, how can we remove these images, such as replicate images, from the models? Okay, and I think in Europe they have a very strong consumer protection laws. They've been saying so every consumer can ask the company to remove the data from their software. Even they're allowed to use it maybe last month, and then later they change their minds. They can request any company to remove the data from their platform. So this is called the right to erasure, the right to forget the user's information. So now let's give an overview of how diffusion model works before we go to removing concepts from diffusion model. Diffusion model is actually very easy to implement. Yes, you have a forward diffusion process, which is fixed. You try to add some Gaussian noise, and you have a thing called reverse denoising process, or the reverse diffusion process, which you try to learn to gradually remove the noise. So you go from noisy images, and you try to remove some amount of noise and try to get a cleaner images, less noisy images. So if you just apply this process over and over for like 100,000 steps, you will get a very clean images. Okay, and in training time, we have training images, and we sample a text prompt, and we add some noise to the images, and with some kind of predefined coefficient between 0 to 1. So if alpha t is close to 0, you just add more noise. If alpha t is close to 1, you just add less noise. And then you get a noise images, and feed these noise images to the network. It can be a unit, can be a transformer, and you take a text prompt like a basket of flowers, and the network's job is to learn to predict noise, to minimizing the L2 distance between the predicted noise and added noise, right? So it's just L2 minimization problem. It's fairly straightforward. And now, one idea to remove Grumpy Cat from these models is we can just go to this website called haveibeentrained.com. You can actually go to this website. You might have been trained. You can search your name or search your photos, right? So I have to report I have been trained by these models. And you go to this website, just type Grumpy Cat, and you find a bunch of Grumpy Cat images. Not everyone. I'm not sure why is this guy here, but most of the images have Grumpy Cat. And you can remove these images and you can retrain the model from scratch, right? We can remove all the Grumpy images and retrain the model from scratch. But this process is very slow, right? Retraining a model may take you a week, several weeks. It might take you $500,000, several million US dollars, even more than that. So this principle this should work, but it's a very expensive process. Okay. So another idea, which it's a very simple idea, is so if minimizing L2 loss is learning the concept, we can add a negative sign to L2 loss, so we can maximize the L2 loss, right? You just add one character and solve the problem. This is a common practice in machine learning literature. This kind of doing something. For example, if you maximize the loss, now these are two images. If you maximize the loss, you will forget the Grumpy Cat concept. But unfortunately, if you maximize the L2 loss, it also will damage other kind of innocent cats, right? This is not a Grumpy Cat, but it got affected as well. So you become every cat become like average cat. Okay, so and you keep maximizing L2 loss. The L2 loss is unbounded, right? It can go to infinity, right? It's not. It can be as large as possible. You will get like a very huge L2 loss, and you will generate a very random stuff, any type of prompt you are typing. Okay, so you need to do some early stopping. Maybe only maximize L2 loss for like 100 iterations. It's very hard to know when you should stop. Okay, so it's not that easy in some sense, this problem. But the reason why it's become so difficult, I will talk about in a minute, is in some sense, right? If you have a social media platform, like if any kind of social media platform, video platform, like TikTok, this kind of platform, it's actually a common practice, right? If you want to remove your video from a video platform, video website, you can just say, I want to delete my videos, right? You just click a button, and if your video somehow becomes like a viral and like 10 million, hundreds of millions of views or likes or whatever, comments, the company will share the revenue with you, right? You might be able to make a living out of it. You become a content creator, you can make a living, maybe a good living out of it. Okay, so it's a very common practice to share the revenue with creators. It's a very straightforward to remove anyone's video posts from a website. But now things become very complicated because we have a generative models. So the generative models were trained on these billions of user images and generate a test image. And it's the test image who are being consumed by the consumers, right? So the test image might go viral and the test video, generative video might become popular. And it's not the training data was not being seen by the consumer directly. Okay, and this training is very complicated because you're training a model on a model with billions of parameters on billions of images. The training is very complicated, and the test inference is also very complicated. Most model, like diffusion model, which involves like hundreds of or maybe 10 or hundreds of inference steps. So it's not a one-step model. So the inference is also very complicated. So as a result, it's very hard to trace the impact from this test image to individual training images, which makes these things very difficult to understand. Okay, so our idea is since we cannot so many things, so many factors, maybe we should just consider change a very small amount, make minimal changes to this procedure, and then we try to observe what will happen, right? So we try to change one thing at a time. Okay. So one solution here is we, instead of generating a grumpy cat, we can ask the model to generate a cat, right? Each time you type a grumpy cat, the model will generate a cat instead. Okay. So we can override this grumpy cat with some called superclass, which is a cat. Okay, so in short, we would like to minimize the distribution gap between the grumpy cat distributions and cat distributions, right? So here is the, this is the fine-tuned model, this is grumpy cat captions. We try to make sure it's closer to the pre-trained model with cat captions. Okay, so and I will skip some details, but minimizing the KL divergence is equivalent as minimizing the L2 distance, right? So basically, we try to say if you feed a cat captions to a pre-trained model, the network should output something similar as you were feeding the grumpy cat captions with fine-tuned models. And since this requires to load two models, we would like to make it simpler by pretending the pre-trained model as we replace the pre-trained model with the fine-tuned model with stop gradients. So we only need to load one model to the GPU memory. But if you have a very big GPU, you don't need to do that. And since generating images in diffusion model is very slow in the training time, we just generate a bunch of images X, and we try to add some noise later to simulate the XT, which is the intermediate step of diffusion model process. So I will skip some math, but the final method is extremely simple. Is you take a cat images, you generate some cats. These are generated, you add some noise to the cat images, and you feed these images to the grumpy cat captions, and you feed the same image, you feed exactly the same image to the cat captions, okay, to the cat captions, and you try to minimizing the L2 distance between these two predictions, right? And we add a stop gradient here, so we would like to make the grumpy cat noise look more like a cat noise. Like we don't want to make the cat noise look like a grumpy cat noise. So there are the stop gradients here. We are free. We only backwards gradients through this branch. Okay. And here is some results. You can see this is the pre-trained model. You remove the grumpy cat. But for other cats like this British short-haired cat, you can almost preserve its content. Okay. And the same apply to these other characters, this Star Wars character R2D2. So here is R2D2. I will show some image which looks a little bit creepy. So there are some content warning. There's a Nemo here, and now you can, after you remove R2D2, you become like a generic robot, or like a delivery robot in some sense. And if you remove R2D2, you remove Nemo, it becomes like a fish. Okay, so this concept is removed. You can also remove certain artistic styles. You can remove Van Gogh style, and here is a kind of a zooming version of that. So you make every artistic style more like a generic. Okay, so and you can also remove certain person. Here is this particular lady's image has been memorized. So if you type this lady's name in test time, it will generate exactly the same training images, right? Here we try to remove this image. We're not trying to remove this lady, we try to remove this particular image. And after you do that, you can make the image, if you tag this lady's name, you generate more diverse outputs. Okay, the same idea here, this is maybe a cover of some computer games. And if you type this game's cover, you will generate exactly the same training images. And if you remove these training images, we can make it more diverse. And another idea, useful thing about these messages can be build more safe models for kids safe model. I think right now, if you're parents, you don't want your kids to be close to these models, right? There are no it's very easy to generate anything you don't want to kids. Like you can generate kids with guns, kids with drugs. You don't want anything for kids for that. Interestingly, in the training time, the model may only learn to generate kids and guns separately. But since the model can compose two concepts together, even you don't have any kids with guns training images, the model can generate kids with guns in the test time because the model can compose multiple things together. And now, after we remove the concept of kids with guns, we can generate kids without guns, or maybe some with some water guns, and we can preserve the kids and gun concepts separately. Okay. Okay. So there are some discussions. For example, there are lots of concurrent work. It's a very active research area. There are some limitations about this method. For example, how do we know if the concept has been removed, or they just hard to find, right? In the model, it's very hard to know what does it even mean something get removed from the model, or maybe it's just harder to generate, but it's still there. For example, if let's say I hide like a key in this big room, and you cannot find the key, but it doesn't necessarily mean the key doesn't not exist in the room. So that's separate things, right? And the other way, how many concepts can we remove? Oftentimes we observe after you remove like hundreds of concepts, the model performance will degrade, which is not what we want. So people are still working on that. And this is also very vulnerable to adversarial prompt attacks. So there are some attacks which can bring back the concept. For example, here you can type we try to remove some adult content, but you can type something like this, which I'm not sure what's the token ID for this one, but this is non-English. Like I'm not sure if it's any type of language, but you can do some adversarial attack. You put this one, and you might be able to bypass this kind of concept removal process. Okay, so that's the first part. Any questions so far? Happy to take some questions for the first part. Yeah, before I move to the next part. Okay, okay, go ahead. Yep. So I'll talk about the consent part, and talk about how can we get people paid, right? Yeah, in some sense, I was actually worried. I wonder if people will still pay for, they might just take our lectures videos and tune avatar. Why do they need to hire a faculty member? For at least for teaching, right? Maybe we are still needed for research. Okay, so we also want to get paid as a faculty member before we get retired. So now, how can we get people paid, right? So if you train a model, on billions of images, like this image, and these test images are actually very similar to the training images. These are training images, okay? And we want to come up with some algorithm called attribution algorithm, which can give us some percentage. Maybe this image should get paid by, let's say you make $1 out of these test images. Someone buy this image for $1. Maybe you can give 2%, 1.75% to this image, 1.5% to this image, and 1.33 to this image, right? So this percentage looks very low, but it's much higher than the chance which is 1 over 400 million images in this data set. Okay. Now, how can we figure out how much percentage we should assign to each image? By the way, the sum of this percentage should be 100%, right? Because you only have a single pie to share. So, and now the question is, how can we, solve this problem? And the most difficult part of this problem is we don't have the ground truth. Nobody can label. We cannot hire humans to label which image has which percentage, right? That's almost impossible. And in some sense, humans are also not very good at giving credits to other people. If you write a paper, I want to ask you how much credits you should give to the prior work and how much credits should give yourself or give your co-authors, and you will have all kinds of interesting discussion around this topic. Okay, so in some sense, humans are also not very good at giving out credits. So now, in most of the foreign projects, all we try to do is to come up with some kind of pseudo ground truth to evaluate and learn attribution algorithms. Okay, without ground truth, even you come up with the algorithm, you don't know how well the algorithm works, right? Without ground truth data in the test time. But if you have some ground truth data in the training time, you can even train the attribution algorithm to make it work better. Okay, so again, we have this exactly the same idea for change one thing at a time. This advice was actually coming from my postdoc advisor, Bill Freeman at MIT. And he always asks the students to only change one parameter in their experiments rather than change 5 things, and it doesn't work, and they don't know which one makes things worse. Okay, so here we just change one thing at a time. We try to add one training images. Okay, so we have a pre-trained model, and the pre-trained model can generate a building, and we can fine-tune this model. On a single building image, this church image, okay, for a long period of time. And now we only fine-tune the model on a single image, and the model will be highly influenced by these training images, right? Because we only fine-tune the model on this training image. And the model will generate something look like this, which resembles some features of these training images, okay? And now if you have a successful attribution algorithm, you should be able to tell me among all the potential training images, this was the ground truth training images we have used in the first place, right? This is a guess which image has been trained. So in this case, we turn the attribution problem into a kind of like a training image retrieval problem, okay, which we can evaluate the retrieval performance. Okay. So now there are a bunch of fine-tuning methods. In our lab, we have a method called custom diffusion, but you can also use other fine-tuning methods such as Jun-Booth and other methods. Okay. So to achieve this task, we just fine-tune lots of different models. Then we fine-tune some like so-called object-centric model. We take a single image of objects, we fine-tune it on this data set. Here, the V star denotes these particular buildings. It's learnable tokens. And we also fine-tune the model on lots of artistic styles, on different styles. We make it this kind of styles. Okay, these are other images. Okay, so we have two types of data models. And in total, we have fine-tuned around 18,000 models and collected around 4 million training and test pairs. Okay. Luckily, fine-tuning a model only, it's only a single image, so fine-tuning a model only takes around 10 minutes. So you don't need that much compute for that. Okay. Now, given these fine-tuned models, we can learn a function which can associate these particular generate images closer to its ground truth training images and far away from other random building images, right? So the idea is we want to learn feature space such corresponding training and test images closer to each other. And this is basically saying that the inference of these training and test pairs should be higher than the inference of this test image and other random training images. And this can be very easily learned through a standard toolbox called contrastive learning. So the idea here is, if you're not familiar with contrastive learning, the idea is very simple. Is we would like to each column is like different generated images. Each row is different training images, and we would like to maximize the dot product between the embeddings of the corresponding training and test images. We want to make it as high as possible. It's like if you normalize the embedding, it's like a cosine distance. We would like to minimize kind of the vector's angle. We want to minimize in the dot product of other random pairs, right? So that's basically what we're doing. Okay. So this is basically this is how it works. Okay. And after we're doing this contrastive learning, we can. So this is the ranking by using some off-the-shelf pre-trained models like Dino, just some computer vision features. And after fine-tuning, with contrastive learning, this red bounding box is the ground truth training images, which has been used to fine-tune the model and generate test images. So after fine-tuning, the ground truth training images has increased its inference score credits by a lot. Another example here, this is using another computer vision feature, extractors clip. And after fine-tuning, the ground truth image appear in the top 5, right? It was not appear in the top 6 in the first place. Okay. And here are more results on generic stable diffusion results. So here is the test images, and here are our model's outputs. Okay. And here are more results. For example, this one is this I don't know what it is. This looks like a kind of tree, kind of monster, kind of devil or something like that. This looks like a very Gen AI images. I don't know, like very creative, whatever. But as a result, it turns out there are actually lots of similar images in the training set, right? It's not like the model is that creative. It's more like the model was trained on lots of creative images, and no. If you have this kind of similar like a Star Wars character, you can see they are very similar training images, right? So without these training images, then the model will not be able to learn to generate particular characters. Okay, and the percentage is very low because there might be hundreds of these kind of characters in the training set. So it's like they're all co-first author. They all have equal contributions, right? So to these particular test images. Okay, so if you only have one or two images, that image will have very high percentage. But if you have like hundreds of similar images in the training set, they all share the revenues among each other, which is fun. Maybe they are from the same company, we can evaluate our model performance in the retriever, and this x-axis is object-centric models, and the y-axis is kind of artistic-centric models. And we can see, there are some very popular object detection backbone model works pretty well for objects. Clip is fine-tuned with the language and text model, so it's something in between. Okay, this is the pre-trained feed models, but after we fine-tuning the features, every model features has improved after we apply this contrastive learning fine-tuning stuff. And now the clip actually works pretty well for both objects and also the artistic style. Okay, so there are some discussion, there are some limitations. We make things very simple. We simplify a lot of things. We cannot ignore the pre-trained training set. We only study this kind of add-when training. So in some sense, we are developing an attribution algorithm for fine-tuning tasks. But does this our method apply to the generic setting? We don't know yet, right? And lots of papers in the early works in economy, they were studying removing images. For example, if you have the very simple concept is a landmark concept in economy, and the idea here is we can train on random subsets, and we analyze which subsets works best. But basically, let's say you have 10 NBA players. You are in learning an NBA club, and you have 10 players, or maybe you have 12 players, and you would like to figure out how much money you should pay to each player, right? So one thing you can do is you can send 5 players to the court and see which 5 players will win more points than their opponents. And if one player, when that person is in the team, their team is always winning, maybe that player should get a higher salary, right? So you just sample five player subsets out of these 12 players and just keep doing that until you figure out which player has the kind of highest winning contribution in some sense. Okay, so this works for this NBA team to some degree, but now we have billions of images, so you can't just do this random subset. It's very expensive. Okay, another idea here is from Stanford is called inference function. We'll talk about in a minute. Is they try to have a linear kind of like approximation. There are lots of Taylor expansion to approximate the removal images from the training set. But in general, evaluating attribution is very difficult in the general settings because we don't know the ground truth in the general setting. We only know the ground truth in the fine-tuning settings. Okay, so this is kind of Shapley value method. This is theoretically it's the best method. Basically, you just create lots of subsets. So what if I train the model on these subsets? One subset 2, okay? But the issue here is you can, once you fine-tune on different subsets, you can analyze whether the model can still generate these test images or not, right? Whether the performance has dropped for these test images. Okay, so this method should work, but if you have infinite amount of compute, right? But unfortunately, the N here is like a billions. It's not even 10, it's billions. Maybe it works for 10. Unfortunately, in most of the universities or in most of the companies, you cannot even train a single model. Right? You can't even train N model. You can't even train one model. If training one model takes millions of dollars. So this method is not feasible in practice. So what people often do is, what we will do is, one thing you can do is you can apply this machine learning. You can try to remove this image from the model, and you see whether the unlearned model can still generate these particular test images. So you first apply machine learning on individual training images. And then you try to see whether this model can still reproduce these test images or not. The DC method is also very slow, right? Because you have to apply machine learning for n times, which n is a billions, right? And you have to store the weights. You have to store. I mean, you can do some low rank stuff, but you still need to store like even each weight is 100 megabytes. You have to store billions of 100 million model differences. So it's very slow, so the method we propose is we would like to remove the test image. We remove this test image, which is kind of counterintuitive, but we remove these test images. And we call test image Z hatch. And if we remove these test images, we're using some machine learning method by maximizing loss while also minimizing loss on the original data set. And this can be approximated by this loss called EWC loss. Is basically if you ignore this matrix, this is just try to say this is L2 norm. You try to say your new model's weight should be very close to my original model's weights. Right? You shouldn't change the model weights a lot if you don't have to. This F was just called Fisher information. It's trying to kind of measure the gradients of the loss with respect to the weights, and try to, so you have two, you have some gradients vector, and they try to compute the kind of the co-occurrence of these gradients. It's how each two parameters interact with each other. Okay, but if you can also just, in some sense, you can also just ignore this term and just basically on L2 norm. And we use this machine learning method, and we unlearn the model once, and we try to evaluate whether the unlearned model can still produce reasonable training loss for the training images. Okay, you can compute generative model like diffusion model training loss, like add some noise, remove noise, and this is the original training loss on these training images, and this is after we unlearn the test images, the loss of the unlearned test image on these training images. Okay, and you can see if you unlearn the model from these bedroom images, you will create a huge difference in the for the training bedroom images, and it doesn't change a lot for the other mountain images. Okay, and now once we have these kind of attribution scores, we can evaluate the method. So here we try to have a more serious evaluation. Is by evaluating method we can remove the top K, maybe top 500 most inferential images, and we can retrain the model from scratch, and we see whether the model can still generate this test image or not. This is just for evaluation. This is not for the algorithm. Okay, and of course this is very. So the idea here is if we can figure out what's the most critical images, we can evaluate whether the model can still generate these test images or not. So one thing we can do is, again, we can check the diffusion model's loss. We can also try to compute some kind of reconstruction loss between these two images. Okay. This is a very expensive evaluation because each time you have to retrain the model from scratch. You need to remove the top K images and retrain the model from scratch. So this is very expensive. So we only do this study in kind of like a medium scale data set, right? With like hundreds of thousand images. We cannot afford to do like on billions of images, right? Okay. So, but we're still doing that. Here that is the results. Here the test image, and this is our method. This is some feature-based methods based on pre-trained features. This is an inference function paper from MIT. And here you can see we can remove these images, remove the top 500 images of each method. We can train the model, retrain the model without the top 500 images. And you can see the difference. So after remove these images, with our method, the model is no longer able to generate exactly the same training images, but with baseline method, the model can still generate something which is very close to the original test images. Okay? Here another example, these skin examples. You remove these images and you see whether the trained from scratch model can still generate these images. You can see our model remove this particular image better than baselines. And we can do this study for different kind of methods and over for lots of test images. So here, this is a random curve. You just remove random images randomly, like you remove 90% of the images, 100% of images, and here is the loss change in the diffusion models, right? If you remove more images, your diffusion model loss will change more, right? And here is our method. We remove 4,000 images. This plot is very hard to see. So one thing we can do is we can check if you remove 4,000 images with our method, how many random images is this procedure equivalent to? Maybe it's as you were removing around 90% of the training images, okay, randomly. Okay, and here you can this plot. This is basically this plot. It's just this number. We'll just read out this number. It's around 80, 90,000. Okay, and here are different baselines. So if you just compute some feature difference, you compute some features and do some nearest neighbor search, you get something decent. But no, if you look at this 500 images, this is only half of the leading method. So this means attribution is more than just doing nearest neighbor search. And you can use our previous papers. It helps a little bit. And this is the inference function papers. And our methods was outperforming all these methods and very on par with the latest inference function paper method. Okay. And our method here are more examples. This is the most influential training images for this particular test images. And you can also click a region, and this is the most influential training images for this particular regions. Okay. Okay. I want to quickly summarize this part. Yes, we would like to, in an ideal world in the future, we would like to enable creators to opt out from the models if they don't like their images to be trained. Or they can decide to, I want my model to be trained on, but I want to get some incentives. I want to get some revenue sharing from these big companies. Okay. So as a result, we can create a framework which creators and generative model can coexist. I think right now the world we are facing is the generative model is eating the pie of the creators, and they don't have very good feeling about generative models. But we want to live in a world which creators can contribute to very high quality images to the generative models, and they can also make a living out of it. So right now, lots of artists, artists, they don't even upload their artwork to internet. You need to go to the museum, and you cannot take a picture. So that prevents their work to being trained by these models. So they don't want to digitalize their work, which is kind of anti the trend of instant digitalization, right? So I want to show some other projects very quickly, if I can. I still have a few minutes. So which is not related to this talk, but I want to show some other projects which we're working on at CMU. So one thing we have been working on, we're working on this kind of text to texture generation is we can add texture to a 3D mesh, right? You can type a text prompt, and the same texture is a relightable texture, so you can relight the texture with different lighting conditions. Right? It's not just only the diffuse component. Okay, and this has been used. I'm not sure if you have played this game before. I'm not sure if that's popular here. It's kind of like a Minecraft kind of game. And so our paper has been integrated in the studio. So if you go to the studio, you can search something called texture generator, and you can type a text prompt, and you can add this texture to the software. Okay, and we're also been working on called generative models for real world. I think most of generative models nowadays are working on the digital world. You can generate a chair image. You can generate a video, you can generate some 3D assets, but you can not sit on the chair you generate here, right? So now we try to, one thing we've been working on in the CMU is we try to have robots to do some painting. We want to create a real painting, what you can send your friends as a gift. You can put on at your home. And here is we create a system which humans and robots can create artwork together. Okay, and we deploy some of the system into the nursing home or hospitals, and it's very popular because people just try to spend some time with robots together. And we're also working on this project called Brick GPT. Is we train a large language model to generate this kind of like brick structures like Legos, and we'll give you some instructions, and you can assemble them by yourself, or you can have a robot to assemble them, or you can have some color version of it. Okay, and we want to make sure the generated structure is physically stable and also buildable. You can actually build it in the real world, not just in the digital world. But to prove that it's buildable, we actually have some robots in CMU to build it for just to show that it's actually kind of buildable. Okay. But you can also build it with your hands, right? That's probably more fun. Okay, and these are more results. So I think maybe in the next 5-10 years, it might be possible if you type a text prompt and someone can ship a product, a chair or sofa or toy to your home, designed by yourself. Okay. Take some time. We're also working on efficient generating models, but the generating model is very slow. Like if you try to generate a video, it often costs you like 50 cents. Like so if you generate 5 videos, you spend like $2-3. So the generating model is very slow to run, and we're trying to make it more efficient. So one idea here is we can try to make the model. We can distill a diffusion model into a one-step model. So it only takes 1 step rather than 50 steps to generate images. So this is the samples from our conditional game model. And it only takes 0.1 seconds per image on A100 GPUs instead of like several seconds. And we're also working on quantization with Professor Song Han's group at MIT. Is we can quantize the model to like int4 formatting, and this allow us to reduce the latency by 9 times. It's especially useful for consumer grade GPUs like A 4090 or like 3090. So basically, consumer GPU does not have that much GPU memory. So this allow everyone to run the diffusion model on like a laptop. Okay. I want to thank my student and collaborator, and Rupert Shenyu did most of the work I just described. And I would like to thanks for your attention. Thank you. Yeah.
Stand Jun-Yan for next talk.
So there's a sparse coding model where when we see a face, there's only a small group of neuron fires.
Mhm.
So my question is that suppose you try to forget about that grumpy cat, and you compare the two sets of the parameters, one with the grumpy cat, the other without.
Mhm.
Do you see any evidence support the sparse coding?
Yeah.
Or do you expect to see any evidence?
I think that's a great question. I think most of the paper, when they are fine-tuning the model, they actually using some low rank like structure. So they only fine-tune like a low rank matrix. So in some sense, they are kind of enforce some kind of sparsity. But there also recent work which shows if you can like identify which neuron was responsible for certain concept, and if you remove them, it also works pretty well. So it's true if you can, it's possible. Most of the time, we only need to change very few neurons.
Yeah. So if that's true in your model, then it's very easy to.
Yeah. There's some more recent work we're doing that more effectively than our original method. Thanks for the question.